In this video, we will explore some features, common uses, and operation of a rheometer. A rheometer is an instrument that can apply forces or strains to a small sample and measure the resulting displacements or forces. Samples are typically measured dynamically, and the method varies based on the test being performed. Rheometers also feature systems to control the temperature of the sample and the environment which it is exposed to. Some examples of material properties that can be measured include viscosity of liquids, viscoelastic properties of solids, and the influence of temperature, time, and strain rate on these properties. Viscosity is a measure of a fluid's resistance to shear deformation. Fluids with high viscosity will require more force to deform at a given rate. In the context of a rheometer, strain rate, or more specifically shear rate, is defined as seen here. Rheometers typically produce shear deformation by constraining fluid in between two surfaces and translating the surfaces relative to each other at a measured velocity. The shear rate is defined as the velocity of one surface divided by the thickness of the gap between the two surfaces. Fluids which show a linear relationship between shear deformation rate and shear stress are known as Newtonian fluids. Some fluids have viscosities that depend on the rate of deformation, which are known as non-Newtonian fluids. These fluids may have higher or lower viscosities when they are deformed at different strain rates. In the context of composites, resin viscosity as a function of time and temperature is a common property that can be measured with a rheometer. Resin viscosity decreases as temperature increases and will increase as degree of cure progresses. After resin begins to gel and is no longer liquid, its elastic properties can be measured. These properties can be used to simulate and optimize processing parameters of fiber-reinforced composite parts. The viscosity of single components of liquid resin can also be measured, which can be used to select resins for certain applications involving liquid resin processing. The melting characteristics of thermoplastics can also be characterized with a rheometer. As thermoplastics heat up and begin to melt, their stiffness drops until they become liquid. As temperature continues to rise, viscosity will drop until the material begins to degrade. This information is useful for modeling the processing of thermoplastics and thermoplastic composite materials. A rheometer can also measure similar properties as a dynamic mechanical analyzer or a DMA. A rheometer can be used to apply forces or displacements to a solid sample dynamically, for example with an amplitude following a sine wave pattern, to analyze the viscoelastic properties of the material at different temperatures, typically in shear. A rheometer consists of components that can impose and measure stresses and strains on a small sample of liquid or solid material. A variety of test geometries can be used for different samples. Parallel plates, cups for liquids, or fully contained cells for volatile samples, and many other sample containment systems are all available. These components are known as sample carriers, measurement systems, or test geometries. The choice of measurement system is driven by a few factors. For volatile liquids, a geometry that minimizes surface area exposed to the atmosphere can reduce the effects of evaporation on the test sample. Viscosity readings can be affected by evaporation of the liquid during the test. Parallel plates with a large diameter can reduce the ratio of exposed area to sample volume. A cup and bob can reduce the amount of exposed area further. Different measurement systems can require different volumes of sample. Parallel plate geometry can produce results with a very small sample volume. Other geometries may require larger volumes. Samples which contain particles may not test well with cone plate geometry, since the particles may come in contact with the testing surfaces and can upset the measurement. Very thin liquids can benefit from systems which shear large areas of sample. Cup and bob systems may produce more precise results when measuring thin liquids as long as a large volume of sample is available. Larger diameter cone plate and parallel plate systems may be desirable as well, with low viscosities to produce measurements using a larger portion of the measurement range of the rheometer. Conversely, high viscosity samples may require small diameter measurement systems to keep the readings within the range of the rheometer. Approximate calculations can be used to estimate which measurement system may be appropriate for a given test, but it may be an iterative process to select the most appropriate measurement system for a sample. We will select a measurement system for testing a resin sample shortly. A consideration especially important when processing resins is the ease with which measurement systems can be cleaned. The more complex the geometry is, the more difficult it may be to clean in between samples. Disposable, single-use carriers are also available for materials which may not be feasible to clean, such as resins which cure solid during the test. Simpler measurement geometries are typically less expensive, with parallel plate disposable systems being especially prevalent. The selected measurement systems are installed in the rheometer spindle. The rheometer spindle's angular position is precisely recorded with an optical encoder. The vertical position of the spindle is also precisely measured and controlled to maintain a constant and accurate gap between the measurement geometries. This ensures consistent and repeatable results over a range of temperatures. The exact mechanism is proprietary to manufacturers but can involve electromechanical systems which measure and maintain position without interfering with torque or force measurements. Torques are applied to the sample with a precision electric motor. These motors are optimized for low rotor inertia and precision positional control. The torques required to deform the sample can be measured via motor electrical currents. An environmental chamber can be used to control the temperature of the sample while it is being tested. Environmental chambers flow heated or cooled gases around the sample in measurement geometry. The temperature of the sample can also be controlled by a Peltier cooler embedded in the measurement geometry. The temperature can be held constant or can be increased or decreased to observe properties as a function of temperature. The viscosity profile of a prepreg resin system as it cures is a common measurement that can be performed with an environmental chamber and disposable measurement systems. We will now use the rheometer to measure the viscosity of a liquid epoxy resin. We will measure the viscosity over time as it cures from a liquid to a gel to a solid. This test is useful for comparing the suitability of different resins for certain manufacturing processes such as resin infusion. Datasheets often contain information regarding resin viscosity, but in some cases additional data may be required for a specific application. The ASTM standard that is often referenced by epoxy resin datasheets uses a viscometer to measure viscosity, a lower-cost instrument that produces a less complete materials characterization. We will use a rheometer to more closely control shear rate, which may or may not be necessary depending on the application. With the rheometer, we can use the measured torques required to deform a sample at a measured strain rate to calculate for viscosity. The measurement system geometry is also required, and using these equations we can determine the viscosity of our sample. We will use a disposable 25mm parallel plate system, a general-purpose geometry suitable for measuring medium viscosity liquid resins while curing. Our plate gap will be 1mm, a common gap size for samples where available sample volume is not a constraint. We will aim for a shear rate of 100 per second, which can correspond very approximately to liquid composite processes. The shear rate depends on many factors and will vary by orders of magnitude depending on process parameters. To achieve a shear rate of 100 at a plate gap of 1mm, we will select a velocity of 100 mm per second at the edge of the plane. This requires 1.27 rotations per second. The shear rate throughout the plate will be lower than this value due to reduced effective radius, and this is accounted for when we calculate viscosity. For this test, we will maintain a temperature of 25 Celsius to replicate a room temperature cure. It is very common to characterize materials at different temperatures, which we will do later in the video. This rheometer is not currently fitted with an environmental chamber. Instead, it is fitted with a temperature-controlled lower plate which controls the temperature of the sample through contacting its lower surface. Two ways to measure viscosity are by continuously rotating the upper plate or by oscillating it back and forth. Oscillatory movements can provide insight into the behavior of a solid material or resins that have gelled, but since we are testing liquid resin in the context of liquid composite processing, we will rotate the plates continuously to more closely replicate continuous flow of resin through a medium. We will install the disposable measurement system and program the test. We will prepare the resin per manufacturer's instructions and dispense into the rheometer measurement system. It is important to ensure that a correct amount is dispensed so that the edges of the sample are following guidelines. The sample should not be overflowing or underfilled to avoid inaccurate readings. We will start the test. We can see that the viscosity rises slowly for the resin's working time and then increases progressively faster until it gels and the rheometer can no longer reliably produce a measurement. The data from this test is available for download at the link below. Using the measurement geometry that was used here, the viscosity of the sample can be calculated. This data can be used to inform liquid composite processing such as resin infusion or other manufacturing processes that involve liquid resin flow. Another common use of the rheometer is characterizing thermosetting resins which cure when heated. These resins are commonly used in prepreg fiber composites and adhesive films which are cured in an oven or autoclave. The heated cure cycle can be replicated with a rheometer environmental chamber or temperature-controlled measurement geometry. A heated cure cycle typically involves a ramp up to temperature, followed by a hold for a length of time at cure temperature and a ramp down to room temperature. The viscosity of the resin as it ramps up to temperature and begins the hold is of interest when designing processes and selecting materials for an application, as well as troubleshooting defects. Now, we will use the rheometer to measure the viscosity of a sample of epoxy film adhesive which is cured with a heated cure cycle. To adhere two components together, it is usually necessary for the adhesive film to reduce in viscosity and flow between the two surfaces to ensure that a good bond is produced. Our adhesive film sample is supported, which means that it contains a very thin layer of fabric which provides some structural integrity to the film while it is being handled and placed. It is possible that this reinforcing fabric will affect the test result. Adhesive films are sometimes available with or without a supporting fabric, or may only be available in one form. This particular resin film has a very high viscosity at room temperature and has a thickness which is not easily changed. We cannot set a gap height of 1 mm between the two parallel plates the way that we did with the previous sample of liquid resin. Instead, we will set a constant normal force for the rheometer to maintain. The plates will squeeze the sample with this force throughout the test to ensure that they stay reliably in contact with it. If this value is too low, the plates will not reliably stay in contact with the sample. If this value is too high, the resin may be displaced from between the plates and drag along the edges of the measurement geometry, similar to an overfilled sample of liquid resin. We will also set a torque value that the rheometer will maintain on the sample. If we had set a relatively high shear rate like we did for the previous liquid resin test, the rheometer would not be able to produce enough torque to twist the resin film at the programmed rate. Another way the test could be conducted is with a relatively low shear rate that requires a torque value small enough for the rheometer to produce even at room temperature when the resin has very high viscosity. The sample is loaded and the test is programmed. As the test progresses, we can see that the viscosity drops considerably as temperature increases. It then begins to rise as the degree of cure of resin progresses. Once the resin has cured solid, the rheometer can no longer produce a viscosity measurement and the test is complete. When we compare the measurement we produced to the curve from the resin film datasheet, we can see that the viscosity we measured is higher overall and did not drop nearly as low as it is expected to. Some instability is also present in our data as our viscosity drops. We can also observe that the gap width gradually decreases and then flattens out at around 0.2 mm but is somewhat unstable. 0.2 mm is approximately the thickness of the reinforcing fabric within the film adhesive. At 0.2 mm of gap width, the plates may have contacted the fabric and caused some instability until the gap width stabilized in constant contact with the fabric. The viscosity measurement may have been affected by this, as the friction of the fabric dragging against the plates could have increased the measured viscosity value. We will now conduct the test with an unsupported sample of the same resin film. This film does not contain any reinforcing fabric. We will program the test with the same temperature ramp rate and torque values. We will, however, reduce the normal force slightly to try to reduce the tendency of the resin to squeeze out of the measurement system. This test produces a very similar result as the supported film adhesive. One notable difference is that there is no instability as the viscosity reaches its minimum. It is also notable that without the reinforcing fabric, the gap width reduces at a rate proportional to resin viscosity until the resin gels and the plates are fixed in place. Throughout the test, the resin is displaced from between the plates to the perimeter of the measurement system, which is somewhat undesirable. Overall, the two viscosity curves that were produced are quite similar. This suggests that the reinforcing fabric had a minimal effect on test results. Both tests had overall higher viscosity than the datasheet suggests. One explanation for this could be the initial degree of cure of our material. The roll of material that the samples were taken from had been used previously many times to fabricate parts and has spent a length of time at room temperature. This resin film must be stored in the freezer at low temperatures. The more time it spends at room temperature, the further the material's degree of cure will progress before it is used to fabricate a part. Our material likely had an initial degree of cure before testing that was greater than the sample used by the manufacturer to produce their datasheet. This would increase the overall viscosity measured during the test. Degree of cure of a material can be studied with a differential scanning calorimeter known as a DSC. This instrument measures the energy entering or leaving a small sample of resin to characterize its cure kinetics. This material may or may not be suitable for all processing applications given its initial degree of cure. Depending on the application, more testing may be required. The manufacturer also does not list the exact method that they use to measure viscosity. The shear rates that produced our measurements may have been higher or lower than those used in the manufacturer's tests. Processes involving film adhesives would likely involve lower shear rates than those present during some portions of our test, and limiting the shear rate to a lower value may produce a different result if our resin is non-Newtonian. In this video, we tested two different resins and recorded their properties as a function of time and temperature. We also studied some of the calculations that translate test parameters into viscosity measurements. There are many considerations when selecting a measurement system and parameters for a rheometer test, and we discussed some factors which may drive decisions.
Thanks for watching. To see more virtual labs and learn more about composite materials, make sure to subscribe to the CKN YouTube channel.